Okay, we are recording our session as always. Welcome again, week 9. This is the week where we're finishing up the neural networks, and then we'll move on to some other topics that I'll mention briefly in a moment. Now, I think if you've spent some time with the neural networks piece, you probably understand why we have the course flowing the way it is, starting with decision trees, which we can all sort of get our heads around, moving into regression, where there's a little bit more work to do in terms, again, transforming, imputing, trying things forward, backward, selection, stepwise, etc. And then we come to neural networks. And of course, the neural networks are the most complicated aspect in terms of options. And so I think it's important that you not say, well, gee, I'm going to learn everything there is about everything in the neural networks module, because it'll drive you crazy. I'm not even comfortable with a lot of it that's in there right now myself, because there's just so much. Now, we talked about how neural networks work in general last week. So what we're going to do tonight is focus a little bit on some of the pieces in SAS that I think are beneficial, although there's an awful lot there. Now, I guess I should repeat this every week. It bears repeating, but I haven't been. But, the SARMA text is quite good. I find it to be excellent on the subject of neural nets. You may not think so. There's an awful lot of math and calculations in there. But if you skip over that and read what he advises you do on certain settings, he gives you a lot of help and a lot of, I think, reasonable explanations as to why you want to set certain things and when to set certain things. I hope to put together something which, of course, I would make available to students present and past, that gives students a little more of a cheat sheet, if you will, as to when to do what settings. But I'm still working my way through building that, so I'm not ready to do that yet. But I'm getting closer, and probably another semester with SAS Enterprise Minor and a little more work on my part studying, I'll have something. So again, if you've not read Chapter 5 in the SARMA book, it is excellent. Again, you can skip over some of the math where he's explaining, all the functions, but he talks about, and he walks you through 2 excellent examples building a neural net, different ways, one with a cost function. And explains a lot of things. I also think, again, I haven't repeated this every week, but I also think many of the help screens in SAS Enterprise Minor are quite informative. They're succinct, but you'll see pieces of them tonight because I find they really give you a pretty good feel. You go in and search on the thing you're interested in. They give you some ideas. And then, of course, the idea is to build on that. So with neural nets, I would say start simple, stick to the basics. Don't try to get too fancy unless you really, really are energized and have lots of time, because there's not an infinite, but there's a large number of combinations you could try with neural nets, a large number of combinations. So we're going to talk about a little bit of that here, not all of it. It's impossible for that. So the agenda. Now, I thought I'd start with some general guidance for neural nets, because people are going to ask those questions and already have been, and then talk a little bit about the neural nets that are in Enterprise Minor, do key settings, and maybe a screenshot walkthrough. I was going to do, like I did with regression, sort of a live walkthrough in SAS Enterprise Minor, but it's been running slow, and my computer's been running slow, so I didn't want to risk that. And then we'll talk about some other things. Okay, general guidance. This, again, right out of the help screens. Before you train a neural network, you may want to do the following. Well, we've seen this before. Sample the input data. Sure, if you have a large data set, obviously you have to sample it. But don't feel like you have to sample if your data set's small. If the sample set is sufficiently representative, then the relationships are okay. Again, if you're sampling. Create partition data sets. This question has come up. Some people have said, my general guidance was you only needed 2 data sets, training set and a test or validation set. With neural nets, although the guidance is still a little mixed on occasion, the best recommendation is to use all 3. So when you partition your data sets, again, the default or the norm, I guess, not really the default, the norm would be kind of a 60-30-10. You see, the neural network uses both the training and the validation sets to actually build the neural network and find out where the best one is. And then the test data set, the third data set, is the one you would test to see how well it works. So you do need all three. You'll see that some of the results when I get to it a little bit later. A third piece of advice, right from the help screen again, use only the important variables. We know that the tendency is to just dump everything in. I've talked about this before. If you have a large number of inputs, you're going to get a lot of confusion there because you need to have a large number of cases with a large number of values for all of the combinations of the inputs to really get a good fit. Now, like it says here, if you know from your business expertise an input's not useful, exclude it. Okay, so you may want to not throw everything in the kitchen sink, especially if you have a large number of variables. Start with a smaller number. It also says when many inputs are available, the choice of an architecture is important. Multilayer perceptron, that's the norm. I'll restart my computer right now. The norm is the MLP, that's the backpropagation of multilayer perceptron with the hidden layer. Tend to be better ignoring irrelevant inputs than some of the radial basis function networks. I don't have to say too much about the RBS, a little bit. Having many inputs reduces the number of hidden units you can use, since the number of weights connecting an input layer and a hidden layer is equal to the product of the number of units in each. Okay? So, again, the more inputs you have and the more hidden units you have in your hidden layer, the more connections you're going to have. And remember, all of those connections have to get adjusted after each iteration, which will slow it down. Now, for the kind of data sets we're using, I don't think it's going to slow it down significantly. None of you are really out there using a Teradata data sets yet. We'll talk a little bit about that in week 11, but not today. But anyway, just some general guidance. So I thought this was pretty good. Again, written well. I highlighted a few things. So again, some more things to consider before you actually go and build it. Transforming. Again, several students have asked, do we still need to transform the variables if they're skewed? Well, again, the guidance is somewhat mixed. Sometimes it helps, sometimes it doesn't. I'll show you again my results tonight. There's not much difference in whether it was transformed or not. But why not try it again? So it says neural networks can learn nonlinear functions and not as sensitive to transformations as regression. Remember, things get normalized on the input level, first of all. So everything's between 0 and 1. So that sort of pulls the outliers in and takes care of a lot of the skewedness. But, you know, but outliers certainly can have as it says, an undue. So you could always truncate some of those too. I mean, if you want to transform things, maybe just get rid of anything 3 or 4 sigma out. That's something to try. Missing values. What do we do about that? Neural network node omits cases from training if any of the inputs are missing. If any of the inputs are missing, that case, that line of data, that's line of data in the spreadsheet or the data file is gone. It will not be used. So you may want, and again, it says may, doesn't it? May want to replace missing data. Okay? Then it gives you some ideas about how to replace the missing data. Okay? So again, these are all tips before you ever get to that. Now, when I said the guidance was mixed, here's a quote right out of SARMA. Okay? Page 242. Variable transformation, this is blah, 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 are done simultaneously in such a way that the error function is minimized. This does not rule out transforming some or all the variables if you choose to do so. If you choose to do so. Remember, the input layer normalizes interval variables, so 0 to 1. The input layer converts categorical variables to dummy variables automatically. Again, assuming you haven't gone through some user-specified settings. So even SARMA is not totally hard over on transformations. And sometimes he does them. Sometimes if you read the chapter 5, he skips them. Not very clear. How about a couple of other things? Again, we're still on some general guidance. The number of hidden units. A couple of people have even asked about that. How many neurons do I put in that hidden layer? How many? They call them units. Each unit is a neuron. And it says the best number depends on the number of training cases, the amount of noise, and the complexity of the function you're trying to learn. Well, yeah, that doesn't help much, does it? Because we really don't know. We don't know much about that. We know the number of training cases. We don't know the amount of noise. Noise is a funny not subjective, but sort of subjective thing. It's the stuff that's in your data that really has nothing to do with the problem. We all have noise in our data, random things that occur, they show up, and it's hard to sort of judge how much noise is in your data. And the complexity of the function you're trying to learn, well, you really have very minimal idea about that until you've actually trained the neural network. You know it's going to be pretty complex, nonlinear. And it says if you're using a neural network, you don't know how much noise you have or how complex the function is. So it's generally impossible to determine the best number of hidden units without training numerous networks with different numbers and just taking a look at the error. Okay, so trial and error. Again, this brings us back to one of the main things that's impressive about something like SAS Enterprise Miner, as well as other high-end software, is that once you have it set up, you can build multiple models with just a simple click. So it says the simplest procedures begin with a network with no hidden units, which isn't really a neural network at all. It's more of a regression equation. And then add one hidden unit at a time. Okay, stop adding hidden units when the generalization error goes up, which is sort of what the software will do in some of the automatic modes. The noise levels can be interpreted according to the following tables. So this is a little help here interpreting noise level. You get a large misclassification rate and a low R squared, probably got a lot of noise in the data, or you've not picked a very good set of inputs. You know, again, if you're using inputs like the shoe size and temperature of the day to predict the price of the stock, you're probably going to get this, and you're probably going to get this. So you're not going to have much, hope, no matter what you do there, because you've got a bad choice of inputs. So again, number of hidden units and noise levels not an optimal value. It's a crude estimate, blah, blah, blah. To get the best generalization, spare with different numbers of hidden units. Okay. So we've answered a few of the questions here. Again, a lot of trial and error, a lot of options with neural nets, many more so than you have with the other models. Why do we want to go through the angst of doing all these various options and various settings and keep trying things and building a lot of neural networks? Because if you have a complex problem, they will usually be the most accurate of the models compared to regression or neural nets. Regression can model nonlinearities, okay. Decision trees, not really model nonlinearities real well, but neural nets, they don't have a problem. Give them enough time, enough training cases, they'll model anything. Okay, so that's a little bit of a general guide. So let's talk about the SAS Enterprise Miner neural network models. This is that table, I think I've shown it before, of all the sort of primary models in SAS Enterprise Miner. We obviously have talked about decision tree and regression, and here's our third primary one, neural networks. There's also a couple of specialty ones that fall into the neural network category. Autoneural, which is really, I think, a primary one. It just automates things. And this strange one down here, DM neural. Okay, and then next week we'll talk about some of these other things, some ensemble models and so forth. Now, where do you start? Well, again, these are your three choices. The autoneural is where I think you probably want to start. Just let the thing automatically do its thing and see what you get. You can adjust some things, number of iterations, etc. I'll go through those in a minute, but you basically have an automated system. It says stand back, boom, boom, boom. Then you can go into the neural network, and here you have a choice of a couple of architectures as well as a choice of many settings. And then there's this DM neural, which is kind of a strange cat that I would say you can go ahead and use this if you so choose and want to see how it does, but I wouldn't tweak too much with the options unless you really understand what's going on there, because it's doing something quite different than the other neural network models. It's doing something quite different. If you look in SARMA and look at page, I think it's around page 309, 310, he explains what's going on with the DM neural as best he can. And it's basically, you know, we're almost, I hate to say this too soon, we're almost with DM neural approaching what we call deep learning, because the DM neural will take the residuals of the first model it builds, which it builds like any other neural network model, and use those residuals as the targets for the next model, and use those residuals as the target for the next model. And then the final model is a combination of all of the outputs it got from the many models it created. That's all I'm going to say about that for the most part. Again, you might want to try it. Well, we talk a little bit here in week 11 or 12 about deep learning. You will see a similarity there, I think. Not exact one for one, but similar. But the main two would be auto-neural with very few tweaks, neural network where you have a lot of possible tweaks, and then this one if you just want to try something. Okay, so the auto-neural, again, that's a place to start. Automated tool, again, I highlighted some things. Optimal configuration, so you don't have to do much here. You pick it and you say basically go. Hidden nodes are added one at a time, which was suggested, right? For each iteration, one estimate vector, one fit vector are retained. Subsequent training is initialized with the current estimate, so the training continues. You can set an adjustable for the max number of iterations. So if you're not getting a good answer, you might want to up that. You have an adjustable setting for the amount of time that it will train. If the thing is just hung up, you might say just train for. Now, in the old days, again, the old days when we were doing these things with many, much less powerful machines. I mentioned I was doing my first one with a Zenith 286 computer at the National Defense University. Those things were so slow, even for a modest-sized neural network, that you had to give them a time to stop and say, give me your best shot. I think most of what we're doing now, the neural network will finish long before you would have ever set a time. But if you have a large data set, large number of inputs, large number of training cases, large number of neurons in the middle layer, then yeah, it's possible. The default combination functions and error functions are used, which is good. No problem with those. Multiple candidate activation functions are optimized and the best ones retained in the model. So it automatically tries some best activation functions. I'll say a little bit more about activation functions, because that's one of the tweaks you can do a lot with. You know, we talked about the hyperbolic tangent being the norm activation function, especially for the middle layer, but you can tweak that. There are many other activation functions that you could try. Again, trial and error is a big part of this, but an understanding of what it is you're doing and keeping track of it is very important. And then he mentioned here you should use both validation and test data to make sure that the network's generalized for your model. So now we're back to saying we need all three sets. Okay, a little interesting there. They also mentioned that the networks are generally not interpretable. And that's the problem. You know, we've always come back to that. How are you going to explain this to your boss? So you'd like to have a good enough grasp of what's going on in a neural network that you can explain it in layman's terms, because if it turns out to be by far the most accurate model for what you're doing, you may want to use it. On the other hand, if it's just a little bit more accurate than the decision tree or the regression, it might be easier to explain those, would be easier to explain those models. So now we're getting into that. Now, this is also the point in the course where I hope, and of course this is only the second time through this course, so I'm still learning as I go myself, but this is a point in the course where you've had enough experience now with SAS Enterprise Miner to know some of the tweaks and some of the ideas. And what you want to do now is begin to step back and sort of not only hit the buttons and make the models, but step back a little bit and try to figure out why the results look like they do, or should they look like what they do, because eventually you've got to translate from just hitting the buttons into what exactly happened here and why, if it didn't come out the way you sort of anticipated, or if you get a big discrepancy between the accuracies of different kinds of models. Why is that? Is this a problem that's more complex and nonlinear and would be better suited for a neural net and so forth? Have you used the right kind of neural net? So we have to start beginning to step you back a little bit from just hitting the buttons and saying, I'm done, I got a model, to sort of hitting the buttons and then saying, now what kind of insights, what kind of learning goes on here? And that's tough. that's a tough one because we're still all focused on so many options and just trying to get the blankety blank thing to work that it is hard to step back and say, let me see what I can glean from what I've done. But sooner or later, we would hope you do that. Okay, now the auto neural network does have a few things you can tweak. You can set the architectures. Now, the architectures is sort of how you build it, right? The multi-layer perceptron, which set of inputs, one hidden layer, and outputs or targets, is the default architecture, but you can set others, okay? So this is the multi-layer perceptron. Inputs, hidden layer, target. Now, don't let these things confuse you. What they're talking about here are different ways of looking at the activation functions, tangent, sine, normal. Okay, of course, there can be different kind of inputs. You can have interval, nominal, and ordinal. Okay, and then there's a target, or there may be multiple targets, remember. You can also have an MLP that is more of a legit, instead of being an interval target, continuous target, is more of a categorical output, and then we put both answers there, and it computes the probabilities of being in pot 1 or pot 2, well, pot 1, 2, 3, and 4, depending on how many pots you have. But this is the basic one, single layer hidden network. Now, you can change that and say, I want to do 2 layers. There was a thought for a long time that if 1 layer was good, 1 hidden layer was good, 2 hidden layers had to be even better, or 3 hidden layers even better. I don't think the world's evidence shows that. I think it shows that 1 hidden layer, most of the time, works just as well, if not better, than multiple hidden layers. Again, that was the guidance when we had to do these things pretty much by hand, because that was a lot of work. But with the power of the software we now have, you might try that, see if that works. And again, you have multiple activation functions that you can vary over these extra hidden layers. This is called a sort of a funnel pattern. And the best activation function is chosen again. They're still in the auto neural node mode. It's hard to say, but you know, once you set the architecture, and you can change that. You can do multi-layer block network. Okay. The hidden layer neurons are added as new layers versus the previous one. The hidden layers are added in funnel patterns. So 3, 2, 1, fewer and fewer. Whereas in this one, we're adding 2 and then 2. If we add another one, still be 2. Okay. And then we have this last one, the cascade network, where the hidden layer neurons are added and connected from all existing and hidden neurons. Previous trained weights are frozen, optimized to fit the residuals in the previous step, similar to the DM that we talked about. So you can see they're all connected to each other as well as being connected to the next layer. Really odd. You know, people keep coming up with many new architectures. If you had any time to go to that wardsystems.net website, and the Ward Systems people have great neural net software. I've used it from a long time. They have Ward nets, and Steve Ward, who owns the company, created his own architectures. And he says for certain classes of problems, they work well. The problem is knowing which classes of problems. So those are, that's the auto neural node. Now, if you go to the neural node, not the auto, we're done with that now. If you go to the neural node, you have lots of control over combinations of things. You can control the architecture. You can control the hidden, these are the key ones, the hidden layer combination function. In other words, how do we combine the stuff coming up from the inputs? What do we do with it after we've combined them? What kind of an activation function? That's that squashing function that turns everything back into numbers between -1 and +1, or 0 to 1, depending. And then the target layer, how does it combine things, and how does it squash things down or activate things? So you have control over all of these if you go to the neural node settings, whereas you don't in the auto mode. So again, architecture. If you're going to go to the neural network node and build one with a little input from you, start with the multi-layer perceptron. Again, each input is connected to a hidden layer node. Each hidden layer node is connected to the output load. There are some MLPs where you have direct connections. In other words, you go from input right to output and skip the hidden layer. Or you do both. go from input to hidden layer, and also from input to output. Really odd, but most of the time you don't do that. Once you're happy with that, you've done quite a bit. If you wished, there are two other good possible architectures you could experiment with. The radial bias function, or radial basis function, I'm sorry, it's available. It is a very, very complicated way to do business, not easily understandable. If you want to read about that, SARMA has about 20 pages on that, outlining the many, I think there's 7 options for radial basis functions. And I'm not sure I understand all of them or any of them totally. You might want to try them, but I would not. I'd stick with this architecture. There's plenty of options to try with this architecture. And then finally, there's user specified. You get to pick a lot of things, you know, all kinds of combinations. And look at SARMA pages 305 to 312. You'll see the many combinations of options you can try as user specified. So for this assignment, again, my general guidance for the majority, if not all of you, would be to stick with the auto. Do the auto for sure. Do the neural node, where you get to do some settings, and use the MLP and maybe a couple of options there. And if you want to do the DMine, see how that compares, that's okay. Start getting into this stuff. And then, of course, the user specified. If you want to try anything there, help yourself. So I'm not trying to limit you. I'm just trying to say it can become overwhelming because there are so many combinations of things. So back to the MLP, which is the one that everybody should certainly use if you're doing the neural node where you get to have some inputs. It is the default architecture. You can have any number of inputs that you want. You can have 1 or 2 hidden layers. You might try with 1. You might try with 2. 1 is the default. You can have up to 1 to 64 hidden units or neurons in each hidden layer. 3 is the default. As I mentioned earlier, it's basically a trial and error approach to what's best. Okay. The default is a linear combination function in the hidden and output layers. Now, what does that mean? Well, remember the picture was the inputs are numbers between 0 and 1. They get sent up this path to the hidden layer multiplied by a weight. And so when I say the combination function, that means they're just added up. So the default is just to add them up. And then the sigmoid is the activation function. It's usually a hyperbolic tangent or something like that is the default for the hidden layer to squash it down and send it to the next layer. But you can tweak some of those. And then exponential activation function for the output layer. Now, if it's a classification problem, you want to change that to logistic. So here's a screenshot. Multilayer perceptron, no direct connections. Remember, you can have those. 3, randomization normal, boom, boom, boom. Default. You can pull down on these and change it if you want. Default. And yes, we always have the target bias and so forth. So that's a good starting place. See how that compares to the auto. Remember, the auto will be testing multiple activation functions. So sometimes this outperforms the auto, and sometimes not. So the architectures, again, that's that. Now the hidden layer combination function, we're going to talk a little bit about these. The target layer is a critical one, can't be arbitrary. If you have a response variable that's binary or even ordinal, you want to set that to logistic, not identity. Okay, so what can we do with the hidden layer? Well, the default is linear. Remember that just adds them together. It sums them up. But look at these other things. EQ slope, EQ radial, EH radial, EW radial, EV radial, and X radial. All very complex math functions. I think stick with additive unless you want to try some just to see. But don't let yourself get overwhelmed with that. So this is what happens in the hidden layer in terms of combining things. Remember, after they're combined, the second thing the hidden layer does is squash them back down into a number between either 0 to 1 or -1 to +1. And therefore, the default there is the hyperbolic tangent. Other combinations, identity, linear, exponential, square, and softmax. You have to read up on what some of these are. Some of them are pretty unique to SAS Enterprise Miner. Again, you want to try some of those? Go ahead. I could see trying exponential or one of the other sigmoid functions. I don't know if I'd ever try square or identity, but they're there. So, what does the help screen say about the target layer? Okay, remember the target layer I mentioned. Target layer is very important. The activation function for the target layer. The default, okay, it says it uses an internal procedure called proc neural, sets the target layer activation function based on the other property settings. So it knows pretty much what to set if you leave it on default. But if you want to put it on one of these others and try it, feel free. Logistic is the and this gives you some guidance. Logistic is the default activation function for ordinal targets with the range 0 to 1. So we use logistic when we have an output there. Identity is the activation function for interval targets. So remember, the default's going to pick the right one. And if you want to try some of these others, go ahead. And it tells you what range for the target variables you could use this for. So you don't want to use exponential unless your target variables can be anywhere from 0 to infinity. You don't want to use reciprocal unless the target variable can have a range of 0 to infinity and 0 to infinity for the square function. So you have a couple there. You can use linear for any of them. So a little guidance there that I thought was pretty good. And again, there's the sort of a screenshot of the settings for the target layer activation function. You can see all those ones that were mentioned on the previous page are there. If you leave it default, it'll probably pick the right one. So there's a lot of things you could try with the MLP, the Multilayer Perceptron. If you get bored with that, want to try some other things, then there's this other thing called the radial bias function. Now, some characteristics about it. You can, again, have any number of inputs fully connected. So, they're all connected to the middle layer, and the middle layer is fully connected to the target layer. There are 7 RBF configuration options. Sarma outlines all of them. Doesn't say a whole lot about them in terms that would mean much or help you much. So I got to do a little more research and try to find additional help for those things. 1 hidden layer is all there is. 1 to 64 hidden neurons. 3 is the default. Trial and error approach. So far, not much different. But it has a different combination functions in the hidden layer based on the squared Euclidean distance. Remember, that's sort of like the hypotenuse, between the input vector and the weight vector. Uses exponential or softmax activation function. So it uses a different combination function, uses a different activation function in the hidden layer. Those are important. Remember, the hidden layer does 2 things. Sums up the stuff from the input layer and squashes it back down with an activation function. So if you want to see some different stuff in action, the RBF architecture will do that. And then linear combination for the output layer to combine things, and it can use any activation function in the output layer. So it has a lot of features there. You just have to sort of try things and see if one of these radial basis functions gives you a better answer. It's going to be very difficult to explain that, but you might have a case. Okay, so then let me show you sort of what I did. I took this same data set we've used, sort of the same data set, the PVA 97NK is almost the same as the donor set. Has demographic gift. We've seen this before, so we don't need to review that too much. And then the business problem. As you know, you'd like to mail out for the people that are likely to give you the money, and you'd like to predict a couple of things. Remember, there were 2 target variables. One was to predict whether a person would donate or not. That was a logistic function. The other was, or a classification, yes or no. The other was to predict how much they were going to give. And so that was a sort of a continuous or interval function. So in this one, I picked the interval, okay? And the original data had 5% responders and 95% non-responders. The sample data, which is what's being used here, is 9,686 cases, is 50-50. So it's been smushed to give you a better hope of being able to guess or predict how much people might give. So that was the basic inputs. We've seen many of these things before. As you know, there's a lot of variables, and then two targets, target B and target D. Okay. Then what? I partitioned the data, 60, 30, 10. So I did use all three sets. Put partition node in, train, test, validate. Again, it's going to use the train and the validate to build the model, and then test. The test model will determine its worth. They're different than what we've had happen with the other kinds of models. Then what? I tried transformation and no transformation. Okay. Transformation I did pretty much as we've done with other approaches, especially the regression. You know, take a look for the skewed distributions and try to de-skew them, if you will. So this might not be necessary for neural networks, since the activation function also does some of this. Might. It does create new variables, as you know. Of course, it needs to be done for regression and often done for neural networks. So there's one big difference. So I did that, and I ran dual models, one with a transform, one without, of course. Easy to do. Again, selecting the ones for transformations. I picked some of them, not all of them. Okay. All variables with gift in the name were skewed, except the gift time. So those were the ones I transformed. So I transformed all of them. And I used the log function. I was curious as to whether the log function would be adequate rather than using max normal. I was going to go back and do max normal, but I haven't had the chance yet. Okay. Transform variables, skewness went down. Boom, boom, boom. Sure. Okay, then the dummy variables. Now remember, if you have nominal values in there, the dummy variables are created for you. So SAS will create the dummy variables. And so these were created as dummy variables. It combined things too, combined a couple of things. Then imputation. There were a few missing values, I think, as I recall. Yes, there were some missing values. And so, again, if you don't replace those cases are going to get dropped. So you need to do that for both. So for the missing data, I did some imputing. So you can see now I'm up to data set, partition, transform, replacement, imputing. And these were the two. Dem age had a lot of missing values. Gift average card 36 months ago had a lot of missing values, and I used the mean for the imputed variables. Okay, so finally, we get all this done, ready to run some regressions. So I ran regression, the neural network mode, not the auto mode, with the default settings. Iterations was 50. The multi-layer perceptron, 3 hidden nodes, model selection, average error, which of course is the norm for that. You can do other things. And I wanted to see what would happen. Of course, here's what happened. Again, just like before, it's going to stop on the set that does the best, in this case on the validation set. Okay. Still, the training set will still be used later on to compare models and see how they do, but it does stop because remember, it's using both sets of data to train and feedback and change the weights. Of course, the training error kept getting better and better, but the validation did not. And so here was my average squared error. I highlighted that in yellow. So I'm just going to write that number down because I did some other comparisons. And again, the test set, 2, 3, 4, 7, 5, 5. Okay. Interesting to me that it did better on the test set than it did on either train or validation. So again, that could be just the luck of the draw as to which cases happen to go into the test set for such a small data set. I mean, 9,000 cases isn't that much. Okay, so now I said, let me go back and improve the model if I can. I can either raise the number of max iterations so we'll train longer, but you know, I don't think it's going to find anything better. It found the best model pretty quick. Remember, each iteration with new weights is considered a model. So when you look at this thing, each iteration which is using new weights is considered a new model. because it remembers all of those things. You could raise that. You could change the number of hidden nodes. It can be done by hand, or, and I chose to try the auto-neural method. Now, I'm recommending for you, you do it the opposite way. Do the auto-neural first and then try the MLP, but you can do it either way. So you simply attach, I left everything here the same, attach an auto-neural. Here's some things you want to do. Make sure the train action is set to search. The nodes are added according to the architecture. Specify 1 for the hidden units. Tolerance property to low, no for direct. That deactivates direct connections, and no for normal property and sign property. These are a couple of activation functions that I didn't want to use. And here's how that came out. The other one was 234.755. This is 239.61. So about 5, well, not percent, 0.5% worse. In that sense. So it didn't do as well with the auto-neural. Again, I'm looking at the test data for my results here. Now I decided to say, well, what if I didn't transform and replace and impute? What if I didn't do all that? What if I just went partition the data and run a neural network with the default settings? I got almost the same answer. 245,991 versus 234. Now you say almost the same answer, but that's a percent or so, a couple of percent almost difference, and that could be significant. Again, what I wish we had, of course, would be some kind of a business case to put with this in terms of how much money you make and all, and I didn't do that. But Sarma does in his cases, so if you look at Sarma, you'll get some of that. So I tried that. I'm giving you sort of a guideline, a template. You could try what I did with a different data set, obviously, or you can come up with your own way of doing this. There's so many possibilities. Then I tried going back and reducing the number of variables. I just took some out that I didn't think would have much value. Okay. So I took these out. Said, I'm not going to use any of these things. I'm just going to go by basically the gifts stuff and the promotions. Again, sometimes it's better, again, in the real world, where you were working with domain experts, functional people who knew a lot about the data set, clearly you could go to them and say, of these variables, which ones do you really have good inclination or feeling that would not do much good to include in the model? But here, I just took these out here, and I took out these two. And what did I get? Not bad. Remember, this is reduced variables. So these other variables weren't doing much, and the transforming, I didn't do any transforming of this. Just took the original data and took some variables out. 244,326, which is again about a percent, a digit over here in the hundreds column, worse than with the first neural network I built. So again, I'm trying things just to see. Okay, and that's kind of where I stopped. Now, there's many more things you can try. If you go to user specified, there are lots of combos. Starting about page 305, he talks you through, here's all the things you can try. And again, there's such a large number that I think you're better served not to try to do too much with those unless you really are curious. The DM neural, which is again a combo of models, page 309 and on in Sarma, talks about that. It's not hard to set it up, especially if you're just going to go with the defaults and see what that does. Because that is training and converging in a whole different way from the auto-neural and the neural. Okay? So again, just a review, the general process, make sure you have a training and a test data, and in this case, a validation set. Change some of the things, rebuild, keep track of what you've done, try to compare on the relevant measures, try to glean some insights from them. Maybe go back and compare to other techniques you've used. I guess I was a little, I wouldn't say surprised. I was a little interested why no one, when they built their regression model, maybe just one or two went back and said, let me just see how a decision tree would have done with the same data set. Because some of you probably did use the same data sets. So it'd be easy to compare in your paper, here's what the decision tree did. Of course, I'm interested in which one is the most accurate and by how much difference. Because again, if decision trees are close to the right answer in terms of accuracy, they're so much easier to explain and implement. Doesn't mean you don't try everything. Neural network nodes. Use a neural network when you really have a complex situation because you can't come up with a simple mathematical formula. Like a regression model is a fairly complex mathematical formula, but it is a formula. Neural network, you can't really spew out what the formula is. You can't say, well, you take these inputs, you normalize them, you feed them into the middle layer. The middle layer has multiple nodes, it sums them up, then it squishes them back down and feeds it. You can't, how would you put that in a function? You can do it. I mean, you can freeze the weights and run things through there because that's the scoring option, which we can't do with our version of SAS. But okay, prediction is more important than explanation. That's really a highlight of learning that. You can predict pretty well with neural nets, especially for complex functions or complex situations. You cannot explain. You need a lot of training data. Neural nets really like a lot of training data. The hidden layer operations are key, and the target layer operations are key. You have lots of ways of combining things beyond the norm, lots of ways of activating things beyond the norm, although I think there's fewer combination functions that can be any good. There might be some activation functions that give you a bump. And then the target layer. You have ways of combining there, although I don't think they're going to be much different than just linear, summing them up. But there are activation functions, especially important because for classification, you have to change that to logistic. Okay. The most prevalent problem for neural networks is missing values. Okay. Imputation is there. Extreme or unusual values can be a problem. Mitigated somewhat. Remember, the squashing function squashes everything back down between +1 and -1 or +1 and 0. Differs from regressions. Non-numeric inputs pose less of a complication. And unlike standard regression models, neural networks can accommodate nonlinear and non-additive associations. In fact, overfitting is a real danger with neural nets sometimes. So we'll see. Okay, so again, what do you want to do? Look for a good data set. You really need to have a data set that has a lot of cases with a lot of variables. Some of you have done a pretty good job of finding real good data sets. The UCI ones are great for the purposes of this class. Some of them have a lot more cases, a lot more variables than others. So, transform the variables that are skewed if you have time and want to try it. Impute missing values. Try a method for a neural net. The auto-neural and neural, you should try both of those for sure. You're going to create at least 2 models. If you want to try DMine and user specified, go ahead. And even if you're doing the neural net, you could try within that radial basis function and then evaluate the results on multiple measures. Okay? So it's the same process we've been using with a different technique. All of these techniques are similar in the sense that you build multiple models, you compare them on accuracy measures, and you try to grasp a good understanding of what the differences are and why you tried those. And again, it's a little harder with neural nets to figure that out, but doesn't mean you shouldn't try a lot of different options. So finish your assignment, which is due July 20th. And there is assignment guidance, as there is for all the assignments, which basically just outlines what you need to do for the minimal taskings. When we do week 10, we're going to switch gears. We've still got, we said we're going to cover 3 major techniques, and we have. But there's really a 4th technique we're going to talk about called ensembles. And ensembles are, combinations of models. And they can be combinations of the same kind of model, or they can be combinations of different models, or something in between. So we'll talk about that and talk about how SAS handles that. We won't have a specific assignment, but you might want to use an ensemble model approach for your final assignment. There'll be an option there to do that. And as always, and you've been doing a great job here, contributing lots of really good ideas, comments, queries, etc. in the discussion area. I've really enjoyed that. I can't always answer them right away, but they're very good. And we have other people in the class who seem to have some good ideas there and expertise. Okay, as per usual, we're up to the final slide. It says if you have a question you want to ask now, feel free. I didn't want to just keep throwing page after page of option after option because your head will spin. But let me tell you, the SARMA stuff is pretty good. This chapter 5 is very enjoyable. Now, maybe it's because I like neural networks, but I think it's pretty good. And again, as always, we have a let me have any questions area, and we have personal phone calls or emails if it's a personal. Okay, so let me go ahead and stop sharing. I think things are going well. I mean, I feel a lot more comfortable with the class this term than I did last term, where it was our first time through. I'm sure I will feel a lot more comfortable after a few more semesters because there's so much here to digest. And like I say, I'm trying to put together a little, I don't know what they call it, a cheat sheet or guidance that says for each kind of a technique, some of the best things to use for the best, but then you have to say for a certain kind of problem. And that's where it gets a little bit cumbersome. But I'm sort of trying to sort through that because it helps me in the lecture mode. And it certainly, if I get it finished, it would help people, give them some general guidance. Some things you should do, some things you could do. And that's the key, is to separate those and try to figure out when to do which. And that comes with experience too. I mean, this is not something that you take one class using SAS Enterprise Minor and you're ready to take the certification exam. But you should walk away with a very good grasp of at least what's going on with those 3 different major techniques: decision trees, regression, neural networks. Differences, similarities, approaches, kinds of problems they deal with, kinds of things you have to do to make them work. And you should walk away with a reasonable grasp of how to use SAS Enterprise Minor to make those things happen. So I think we're well on our way to achieving that. And what we're going to do in weeks 10, 11, 12, 10 is, of course, ensemble models, so we're still heavily involved in SAS. 11, we're going to talk about text mining, and SAS does have a very powerful text miner. We don't use it in this course. You may use it downstream. I'm not sure what you're going to use when you get to some of the other courses, but they do have a very powerful text miner option. They also have some new stuff coming out that I want to talk about in some advanced options in weeks 11 and 12. So we're going to finish that up as we move along. So there's a lot more yet to take on. But this will finish up looking at the 3 major techniques. And I hope I think most of you have a pretty good grasp now of what they are and what's going on behind the scenes a little bit and how they work, and a good grasp of what you could do in SAS Enterprise Minor to make it happen. Now, you won't have a grasp of all the nuances and the tweaks and all the options because that's going to take a lot longer for both of us to grasp. Okay, well, I'm going to go ahead now and stop the recording.